Hello everyone, I'm Professor Andrew Ray from the University of the Highlands and Islands, and it was my pleasure to be part of the successful Phoenix Project Consortium which demonstrated for the first time the concept of variable buoyancy propulsion in an autonomous aircraft system. Variable buoyancy propulsion has been used successfully in underwater glider ROVs that vary their buoyancy using an inflatable bladder to vary displacement. By combining vertical motion with hydrodynamic surfaces, the resultant force propels the craft forwards. The notion of using this propulsion concept on an aircraft is not new. A patent for it applied to an airship being granted in the US in 1864, but the key to unlocking this idea is the ability to achieve buoyancy variations in a sustainable manner. Previous work by AtheniWorks led to this follow-on project, supported by Innovate UK, the UK's innovation agency, and the Aerospace Technology Institute. The Phoenix Consortium consisted of 4 companies: Bank Sales, IQE, Stirling Dynamics, and TCS Micropumps, 3 government catapults, the Centre for Process Innovation, the Manufacturing Technology Centre, and the National Composite Centre, and the Universities of Bristol, the Highlands and Islands, Newcastle, Sheffield, and Southampton. The 15-metre-long Phoenix prototype was tested successfully and repeatedly along the 120-metre length of a large building in Portsmouth in April 2019, performing approximately 5 transitions between heavier than air and lighter than air on each flight. The Vectran skin fuselage contains the helium lift gas and is kept rigid under internal pressure, and the wings and tail surfaces have carbon fibre spars and ribs. The buoyancy variation is achieved by repeatedly inhaling and releasing outside air compressed in an internal ballonette, which increases mass without changing the displacement. The onboard power system supplies the pumps and valves, the flight control actuators, and the onboard flight control system. A rechargeable battery provides power during darkness, and it is recharged during the daylight hours using arrays of flexible solar cells on the upper surfaces of the wings and tail. The autonomous flight control system manages the sequencing of the valves and compressors to achieve variations in buoyancy to reach specified maximum and minimum altitude thresholds. The successful demonstration of the Phoenix prototype and of a variable buoyancy propulsion system for an aircraft offers a completely different approach to several mission requirements, including ultra-long endurance flight. Firstly, there was sufficient power for the propulsion and control systems from small arrays of solar cells on the wings and tail, resulting in a relatively cheap, almost disposable aircraft. Secondly, the reduced need for motors, large batteries, and arrays of solar cells means that the payload fraction is relatively high. Initial conceptual designs have shown that lifting capability of 100 kilograms to 20 kilometers altitude is feasible. Lastly, the exclusion of motors and propellers means that the Phoenix concept is mechanically and electrically simple. Thank you.